So what are the applications of this Ellingham diagram? Ellingham diagram helps us to select a suitable reducing agent. Just now we saw this will help us to select a suitable reducing agent at appropriate temperature range for reduction. So எந்த temperature இது reduce ஆகும்ன்றது கூட we can able to predict. So the reduction of a metal oxide of its metal can be considered as a competition between the element used for reduction and the metal to combine with oxygen. If the metal oxide is more stable than the oxygen remains with metal, and if the oxide of the element used for reduction is more stable, then the oxygen from the metal oxide combines with the elements used for reduction. So from the Ellingham diagram, we can infer the relative stability of different metal oxides at a given temperature. So we can see Ellingham diagram for the formation of silver oxide and mercury oxide is the upper part of the diagram, and their decomposition temperatures are 600 and 700 Kelvin respectively. இப்போ இதோட applications என்னன்னு பார்த்தோம். நம்ம suitable reducing agent predict பண்ணலாம், and எந்த temperature இது decompose ஆகும் reduce ஆகும்ன்றதையும் predict பண்ணலாம். For example, அவங்க கொடுத்திருக்காங்க Ag2O and HgO வந்து upper part of the graphல இருக்கு. So at what temperature they will decompose means at 600 Kelvin and 700 Kelvin they will decompose. From the graph they are predicting this. It indicates that these oxides are unstable at moderate temperature and will decompose on heating even in the absence of a reducing agent இல்லாமையும் they will decompose. And Ellingham diagram is used to predict thermodynamic feasibility of a reduction of oxides of metal by another metal. Any metal can reduce the oxide of other metal that are located about in the diagram. So for example, இது என்ன பண்ணும் feasibility means what அந்த reaction நடக்குமா இல்லையான்ற feasibility இது சொல்லும். For example, Ellingham diagram for the formation of chromium oxide lies above the aluminium, that is meaning that Al2O3 is more stable than Cr2O3. அந்த graph உடைய பொசிஷனை வச்சு அந்த ஸ்லோப்ஸோட பொசிஷனை வச்சு எது highly stable இது பாசிபிளா இல்லையான்றதையும் நம்ம ஈஸியா predict பண்ணலாம். இப்போ Al2O3 is more stable than Cr2O3. ஏன் அப்படின்னா it is above the chromium oxide graph. So hence aluminium can be used as a reducing agent for the reduction of chromic oxide. அப்போ அலுமினியமே நம்ம குரோமியம்க்கு ரெடியூஸ் பண்ணுறதுக்கு யூஸ் பண்ணலாம். இவ்வளோ datas we can collect from this graph. So however it cannot be used to reduce the oxides of magnesium and calcium which occupy the lower position than aluminium oxide. So aluminiumக்கு மேலே உள்ளதெல்லாம் நம்மளால யூஸ் பண்ண முடியும், அதுக்கு கீழே உள்ளதெல்லாம் நம்மளால யூஸ் பண்ண முடியாது. The carbon line cuts across the lines of many metal oxide and it can reduce all those metal oxides at sufficiently higher temperature. இப்போ we have seen so many graphical slopes here. ஆனால் இந்த சென்டரில் இருக்க நடு லைன் மட்டும் சென்டரில் கட் ஆகுது. அதோட இன்ஃபரன்ஸ் நம்ம பார்க்கவே இல்லை. அதோட பெஸ்ட் part is it can reduce any metal oxide. So that is the best part of this carbon dioxide. So the carbon line graphல centerல கட் ஆகிறதுனால there is some reason behind that for it to go like that, and it is also used as a reducing agent for reducing any metal oxide. We will see what it is. So let us analyze thermodynamically the favorable condition for the reduction of iron oxide by carbon. So இப்போ iron oxide நம்ம carbon யூஸ் பண்ணி reduce பண்ண போறோம். So Ellingham diagram for the formation of iron oxide and carbon monoxide intersects at 1000 Kelvin. You see in the graph iron oxide and carbon monoxide at 1000 Kelvin they both are getting intersected. Iron oxide, can you see here? Can you see it here? Iron oxide is just above that red color line, and carbon monoxide is also intersecting at the red color line at 1000 Kelvin. They both are getting intersected. So below this temperature, the carbon line lies above the iron line, which indicates that FeO is more stable than CO. So இந்த டெம்பரேச்சருக்கு கீழே பார்க்கும்பொழுது FeO 1000 கெல்வினுக்கு கீழே FeO is more stable than CO, and hence at this temperature range the reduction is not thermodynamically feasible. So however above 1000 K carbon line lies between the iron line, and hence we can use coke as a reducing agent above this temperature. அப்போ 1000 கெல்வினுக்கு மேலே தான் நம்ம கார்பனை யூஸ் பண்ண முடியுமே தவிர தவிர below that we can't use. And the following free energy calculations also confirm the reduction of thermodynamically favored. So from the Ellingham diagram at 1500 Kelvin la iron oxide, so it is minus 350 and carbon monoxide is minus 480. So in the reaction நம்ம reverse பண்ணி பார்த்தோம் அப்படின்னா delta G it is giving plus 350, whereas this iron oxide and carbon if you do it is giving minus 130. So standard free energy for the reduction of 1 mole of iron oxide is minus 65 Kelvin. So this is how we have to predict the temperatures, and from the graph what are the datas we can collect. So it is very useful. Without doing any reactions, theoretically we can predict this. So but there are limitations also. Everything will not be favorable at one stretch, yes or no? There will be some discrepancies in between everywhere. There is an advantage means there will be a disadvantage also. So what are the disadvantages for this Ellingham diagram? So Ellingham diagram is constructed based on only on thermodynamic considerations. Thermodynamical ideas வச்சு மட்டும்தான் இதை கன்ஃபார்ம் பண்ணியிருக்கிறாங்க. இட் கிவ்ஸ் இன்ஃபர்மேஷன் அபவுட் ஒன்லி த ஃபீசிபிலிட்டி, அதாவது இந்த ரியாக்ஷன் நடக்குமா நடக்காதா, எந்த டெம்பரேச்சரில் நடக்கும் நடக்காதுன்றதை பற்றி மட்டும்தான் கொடுக்கும், because it is completely based on the thermodynamical considerations, and it does not tell anything about the rate of the reaction. So rate of the reaction na enadhu evlo speed la இந்த reaction நடக்கும்ன்றதெல்லாம் இதை வந்து டிஸ்கஸ் பண்ணவே பண்ணாது. Moreover, it did not give any idea about the possibility of other reaction that might be taking place. இப்படி தான் நடக்கும்னு மட்டும் தான் தெரியும். இதோட வேறு பாசிபிலிட்டிஸ் ஏதாச்சும் இருக்கா இந்த ரியாக்ஷனுக்கேன்னு கேட்டால் it cannot predict that. And the second limitation is the interpretation of delta G is based upon the assumption that the reactants are in equilibrium with the products, which is not always true. So இந்த பிகினிங்லே பார்த்தோம். அவர் என்ன பண்ணியிருக்காரு, ஹெரால்ட் எல்லிங்கம், he has considered all the reactions to be in equilibrium state. ஸோ ஆனால் எல்லா இடத்துலையுமே எல்லா ரியாக்ஷனுமே ஈக்குலிபிரியமாக இருக்காது. ஸோ இவர் வந்து அஸ்யூம் பண்ணி ஈக்குலிபிரியம் கண்டிஷனில் இருக்க மாதிரி இவர் அஸ்யூம் பண்ணி இந்த கிராஃபிக்கல் ரெப்ரஸன்டேஷனை கொடுத்துருக்கிறாரு. பட் ஈக்குலிபிரியம்ங்கிறது it will not be achieved at every time. So that is also a question mark. If it is not in equilibrium, then our calculation will go wrong from the graph. So it is not possible or applicable to use this thermodynamical principle of metallurgy at any time. So this is what we have completed today. So your questions will be today will be define what is Ellingham diagram, or what is Ellingham diagram, 2 mark question, and then observations from the Ellingham diagram, 1 5 mark question. Learn and write, because observation is very 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 important, and limitations also very very important, which is a 3 mark question. Learn and write whenever you are doing whatever the assignment is. Please learn by heart and write as test in your assignment note, and do self correction and send to me. Thank you.